So generally speaking, your programs are not going to become slower unless you have lots of different things to work with. So generally we are talking about complexity when you have a list of numbers, but it could be any collection of numbers. So let's say that you have a list of numbers, and generally what we care is how many things are in a list. You may have a list of 10 things, you may have a list of 100 things, you may have a list of 1 billion things, which actually can happen. So in this class, you care about the point where it fits in your computer's memory, right? Once it doesn't start to fit in your course's memory, you've been around for a couple of years in the program, come and take my database class, right? So there's a whole different problems that we will talk about. But still, for things that fit in memory, it still matters how many things that you do. So what is a thing that takes time? Any operation in your computer takes time. It takes time to read something. It takes time to check if something is equal to something. It takes time to insert something to a list, access a certain element in a list. These are all relatively single operation type things. So meaning that they are very cheap. But when you have a lot of them, then it is a problem. So we are trying to figure out if I have, let's say, n elements in a list. How many operations, if statements, inserts, updates, things like that, I'm going to do in my program. So, for example, if you have, let's say, 10 things in a list, and if you have a program that basically actually runs in constant time, so generally we write O of 1, just means constant time, then you expect maybe 1 operations. It could be more than 1, it could be 3, but it's just always 3. Okay? So because of that, we assume it's a constant. So when it's a constant, we just say 1, but it could be 3, it could be 5. It just does not change when you have more elements. When you have order of n, that means you actually do 10 operations. You do 10 reads, 10 writes, 10 if statements, 10 times something. When you have order of n squared, you do 100 operations, meaning that 10 times 10, right? 10 squared. The point of all this is that how quickly these actually grow. So now this is actually not helping me, so I'm going to have a slower thing. So I'm going to have n, order of 1, order of log n, order of n, order of n log n, and order of n squared. Right? So if you basically have, let's not say 10 things anymore, let's say 16 things. It will become obvious why in a second. Order of 1 means that it's always 1 or 3 or some number. Okay? Order of n means it's roughly 16. It could be 16 times 2, 16 times 3, but that those 2 or 3 times I don't care so much because it's not a magnitude more or less. And order of n square means 16 square, which happens to be what? 64? 128? 6 times 6 is 4. It should be 64. Okay? 100 and... All right, whatever. This is not why I'm teaching this class. I have a computer, so I don't have to do math. All right. So one of the things that we saw was the binary search, right? In the binary search, you actually didn't have to read every single item in a list. You actually kept looking at one point in the middle, and then when you found out that if it's greater than or less than, you go to the right or you go to the left. So that means you look at the next half point, the next half point. In fact, if you have 16 elements, let's say, you're first going to look at the middle point, let's say 8. Then you're going to look at the next middle point, let's say 4. Then the next middle point is 2. The next middle point is 1, and eventually 0. So in fact, what you're looking for is log of n. So because you're halving the amount of space you look every single time. So because of that, binary search is actually much, much faster. And you can kind of guess how much faster it is, because if you had 16 elements, you will roughly make about 5 comparisons. Okay? So this is generally log base 2 of n. And it is log base 2 because every time you divide the list by half. Right? So you will see a lot of this if those of you who are required to and hopefully want to take it, when you take foundations of computing, you will see a lot of this. So this is log base 2 of n. 16 is 2 to the 4, so plus 1 is 5 comparisons. Okay? And n log n, we haven't seen why you have n log n. It still is base 2. It would be something in between, so it will be 5 times 16. Okay? So it is less than n squared, but more than n. So if you actually had, let's say, twice the size of your current list, so instead of 16 elements, you had, let's say, 32. This will remain unchanged, which is great. Order of n log n will be now what? It was 5, now it's going to be 6. Because you basically have one more slicing to do. Order of n is 32, meaning that now this is twice as slow, whereas this is only slightly slower. This is going to be very large, 32 squared. And again, this is going to be somewhere in between, 6 times 32, but this is growing much slower than this one. Okay? And the same thing will continue. So if you double this again, this will be 64. This will be 1, but this will actually be 7. This will be 64. So this is growing very slowly, but this is growing even slower. And then you will have 6 times 64, and then 64 squared is a humongous number. Okay? And it will go going up like this. So n squared will be slower and slower and slower and really slow. Okay? Why do we care about all of this? Well, this is very important when you're looking at your containers. So for example, checking if an element n, let's say item in set, this operation is actually very cheap because of the way sets are implemented. This is actually a constant operation, whereas item in list is actually order of n operation. Okay. So if you have to check a lot of things in whether they are in a collection, and suppose you had to do that n times, if you use a list, you're going to be writing an n squared algorithm. If you use a set, it will be order of n algorithm. Okay? So this is the kind of thing that we will talk a lot of in the remainder of this class. But also to keep in mind that there are different algorithms. So this is order of 1. This is order of n. This is the only one we have seen as binary search. This is generally a double loop. Okay. And this, what we are going to see today, is sorting. Okay. This is a cleanly put in writing. I'm sure it's very clear to everybody. All right. Any questions about this? So if you want to see, for example, this is the search code from, this is not the right search code. Where's my binary search? think I forgot where my binary search is. Let's see. Yeah, I think I deleted that by mistake. All right. I will show that to you next time. So what I want to do today is talk about sorting. Sorting is one of the most common operations, but it is also one of the most complex operations. So very often how many times did we have to write a program where we had to sort something? A lot, right? So one of the first things you will realize as you become now more aware of what kind of programs you can run, sorting is expensive. So if you don't need to sort, then you really shouldn't sort. So like for example, to find the minimum value, you don't need to sort and then find the first item. You can just ask for the minimum or iterate through things to find the minimum. So why is sorting so expensive? Because if you don't write it correctly, and hopefully you will see how many mistakes I will make today, it's going to be very, very costly, okay? Sorting, a naive implementation, is generally order of n square, okay? But the best implementations are generally order of n log n, okay? So the internal sort method that exists in your programs in Python is order of n log n. And on top of that, it's actually implemented in C++. So it's actually quite fast. Okay? So we will never be able to match it because it's actually implemented not in Python, which is interpreted, but it's implemented in C++, compiled. But we can start by first setting up some test code and then trying different ways of sorting. And then you will see how little changes will lead to a lot of speed up. So before I start to kind of talk about different algorithms, let's first write our test code. And I want to show you a different way to do testing. So we have time and random. So generally the way we would like to do something is I'm going to have k, which is going to be the number of elements I have. So I'm going to create a list of 100 numbers. And I'm going to shuffle these 100 numbers so they are in some arbitrary order. So random.shuffle will actually take a list and randomly shuffle. And if you want to see how that looks, we can try it with a few small programs. All right. So all it will do is just randomly shuffle 10 numbers. Okay. Then we want to actually write a method to run the algorithm and figure out how much time it takes. So generally the algorithm we wrote was something like this. That you take some list L. I don't want to change the list because I want to test everything on the same list. So I'm going to create a copy of this. Remember that sort methods actually change a list, so I don't want to change the same list. So I can run multiple algorithms. So I'm going to take the time when I start the algorithm. Then I'm going to run the algorithm here. So for example, L1.sort. And then I'm going to take the time for the end of the algorithm. Then I'm going to print which method something like this. Something like this, all right? Built-in is very, very fast. You really cannot do a lot of damage. Eventually, you will have created such a large list that it will just not fit in memory. But, okay. At which point you have to stop. Okay, so what if I wanted to use the same method for actually testing multiple functions? So this is the one thing that you may have seen come across to. Everything in Python is an object. So sometimes you would say print min, right? And it will get something like built-in function min. Because min is a function, you can print it like anything else. So I can actually use the names of the functions and pass them as arguments to other functions. So instead of really taking just one function, I am going to send the function as an input. And then I am going to call that function with whatever list that I'm running on. Then I am going to print that function's name. This is the same thing as this. Every single object in Python has a name. So I want to now send in, let's say, the built-in function. The built-in function happens to be list.sort. Now, be very careful. I'm not sending the function like this, because that would mean that I want to call the function. I'm actually sending the function's name so that I can access the function. Let's get this slower. Okay. So it happens that the function is called sort, and it took this much time. Okay. So this is a slightly new method, but it's actually a very powerful way to now write more interesting programs where one of your arguments can be another function. Okay? All right, so now what we are going to do is we are going to try to illustrate how sorting works. But for this, I need a number of volunteers to come and line up here. But I have broken chocolate, just so that that I will get some volunteers. So whoever helps me is free to also have some chocolate. This works best in illustration. Do I have any volunteers? Please come. Please come. Come. I think. Please come. All right. So I want you to line up like this here. In random way, your numbers will vary. All right. So, random numbers are all right. I will give you all right. So this algorithm is called Insertion Sort. There is a super boring video on YouTube of sort algorithms represented by Coco dance. It takes forever. They just turn and turn. And it's still this is an abstract algorithm. You will see why, but you will still do that. Okay. So for now, you are combining, right? So you're going to stay here. But I'm going to start with the second term, okay? So I'm going to hold your number for a second, right? So I have 35. I'm going to compare 35 to the next number. Is this smaller? Yes. Shift one. You can either shift the number or the person. All right, shift the number. That's it. There we go. So now I come to the beginning of the list, right? I'm going to put it right here. So what I'm trying to do is I'm trying to make place for this number. Okay? So now you two are sorted, right? So the next thing I want to do is make sure that U3 are. So I'm going to again take this number, 31. 31 is less than 58. Shift 1. 31 less than 35. Shift 1. Alright. We didn't know that. Alright. So now U3 are sorted, right? So the point is that always the first group is sorted. And now you know what to do. Alright, 42. Right? So now there is no point because there is no point to shift at this point, like 42. Oh, you're going to get a lot actually. 7, 58, 42, 7, 31, move it. There you go. You probably are going to be sitting for a while now. Alright, so 55, yeah, 42, right? So I don't need to go further because I know that things are always sorted, right? Larger and larger. Alright, 3. Oh, you're going to get to that. Alright, 58, 55, 42, 35, 31, and 7. Okay? So here's what happened with 3, right? 3 was so small that I have to search for everybody one by one, right? To the left. So in the worst case, if this was sorted in reverse, this would happen for every single number, right? Every single number, I have to shift everybody. Alright, 52. 52, 52, you got it. Alright, you will certainly get all of them. Alright, I have 1. Move it. You will be alright for that one. 28. Alright, this is good. 28. 28. So the point is that for every number, I'm trying to find a place that is the house for 28 and push it in 28. Okay? And 12. Alright, almost there. 12. Okay, so now we're sorted. So let's try to think about what the complexity is. For every number, right? So if I was looking at a number at position 4, what is the worst case? How many comparisons can I make? 4, right? 1, 2, 3. Oh, 3. Okay. So if I'm at location 2, 4, 6, 8, thank you, I'm going to make 7 comparisons, right? So if I have endless, I'm going to make 1 plus 2 plus 3 plus all the way up to n minus 1 comparisons. Have you seen that somewhere else? This is the famous, what do we call that, Gaussian addition, right? 1 plus 2 plus 3 plus up to n minus 1 is what? N squared, n times n minus 1 divided by 2, right? It is actually n squared, right? So the insertion sort, while correct, is actually positive. So now we're going to do one more. Are you with me? Alright, so now you have to first shuffle yourselves. Alright. One. Alright. Alright. So now we are going to do a very different one. For which this is going to be difficult. Okay, so what we are going to do is a slightly different algorithm, but it's called merge sort. Okay? So first, all of you will be in a group of just one person. You'll be all alone. So what I want is kind of separate out a little bit. So I want everybody to kind of be a little further away from each other. All right. Okay. Okay. So think about it that everybody is in a group of one. Okay? What I'm going to do is I'm going to start from the very beginning and I'm going to merge groups in two. So, for example, I'm going to make sure that 7 and 28 are in order, right? So now I'm order. Alright, so you two are now in order. I'm going to stay right here. Then I'm going to make sure you two are in order. There we go. Alright, good. 12 and 42 in order. Okay. We are doing well with the body system. 55 and 31 in order. Thank you. 1 and 52. Depending, you may actually always go on. So you have to be just relaxed. Okay? I'm saying that you have to say. Okay. So what I'm going to do is I'm only going to look at the person in the very beginning of the list. Okay? So that is 3. So can I move it through here? Then I'm going to look at, now you have to go a little further. All right. This is your new list. This is very long. All right. So now I'm going to compare 7 with 58. So 7 will go there. Okay. And 28 with 58. 28 will go there. And then 58 over there. Thank you. Okay. So now I'm going to compare 12 with 31. So 12 will go here. Okay. 31 will go there. 42 over there. And then 55. Okay? Alright, you are being merged, that's good. Alright, so 1, you go over there. 35, you go over there. And 52, you go over there. So the point is that when it's odd and even, right? If you have an odd number of lists to merge, the last list is not merged, right? And in the next iteration, that list is merged with the rest. Alright, so now I have 3 lists left. So this is going to be easy. Okay, so what I will now do is again look at the smallest list. 3 is here. 7 and 12, 7 is there. 12 goes in. Next 38. Next 31. Next 42. Next 55. And 58. Right? So what I'm doing is this stage is called merge. Right? So the merge step is that you always look at the 2 lists and the top of the list. And whichever is smallest, you move that to the new list, and then you continue doing. It may turn out that one list is finished, the other list still has 6, at which point you can put all of that list in the back because there's nobody else to do that. So now I have 2 lists. For this, I'm going to just bring my chocolate. So you can visualize what you do. All right, so now the final list the final merge will merge list. So if you have only 2 lists left, you can have the final merge. So you can give me your number. You're welcome. All right, I have 3. Yes, please. Where's the left here? 7? All right. It's maybe a little peanut for the actual day. So it's like 12 over 35, 12. All right. 28. Thank you. And 31. 35. What do we have? 42? 52. 42. All right. Okay. And 52. Thank you. All right, you guys are all set. So I don't even have to check it because you are already sorted. I wish I was not to run that. Thank you. All right, so do we understand the solver to do? All right, so the next thing we will figure out why this one is cheaper than the other one. But we will have to write them both first, and then do the thing. All right, so our job is to write these 2 algorithms, but correctly, which is not always easy. And then we are going to time them to convince you that they are not so bad. Okay? All right, so let's go over insertion sort. Okay, so what did we do with insertion sort was all right. So basically, at every point, we try to keep the list to the left of where we are in sorted order, right? So if I were to take this value, I will take that value and remember it. And then I'm going to copy the values 1 step down if they are bigger than the value that I have. Let's say this is 12. So let's say I have 1, 5, 13, and 15. So I am going to copy 15 here, 13 here, and here 5 is already less than, so I'm going to put 5 here, 12 here, right? So this is kind of the basic algorithm. Shift things one by one. Remember the value, then you can shift no more, put it in where it is. Okay? As simple as that algorithm is, I also, every single time I write it, after 1 year, I always make a mistake. And when you make a mistake, it comes up incorrect or infinite loop. And so I tried it this morning. This morning, it worked on the 3rd try. So we will try again. So it's like +1, -1. You have to debug it, right? That's what I'm trying to say. It's not like it just comes out of you perfectly. All right. So let's try to write insertion sort. Insertion sort for L. Okay. So I'm going to go from the beginning all the way to the end. I don't need to check the first item because I'm going to start from the second item and compare it with the first item. A list of one item is always sorted by default. Okay, so for R in range of 1 up to length of L. Okay. And I will try to take a lot of shortcuts with these algorithms so they can compete with the internal built-in sort. So one of the things, for example, you can do is range of L will create a list. But if you don't want to create a list, but you just enumerate over it, you can use this function called xrange. If you don't care to learn what that is, that's fine. Because when you say range of 100, it will actually create 100 numbers, whereas if you do xrange of 1000, it is actually an enumerator that, it will just create a number every time you ask it. Okay? I'm just trying to be competitive with the internal sort. So for each I, meaning that start from the first item, compare with 0, start from the second item, compare with 1 and 0, and so on. So I need to first remember what the value is. So I am going to say, this is the value that I'm comparing for. Okay, so I am at this point. I'm going to start checking from the value right next door, right? So I started at 1, so I'm going to check starting with 0, right? So the first value I checked is valid. If you are not careful, you may be looking at the other end of the list, which was not what we want. Okay, so while I is greater than or equal to 0, okay, not I, j. So I'm going to have a second one called j, and it's going to start at I minus 1. So the idea is that here I is 0, 1, 2, 3, 4, right? I is 4. Now j is going to start at 3, and it's going to go this way, right? I'm going to look at this element versus value, then this element versus value, until this point, where this element, I'm going to compare this value. At some point, I'm going to stop, right? I will stop if the value that I'm looking for here is already greater than the value that I'm looking for. So while j is greater than 0, because when I come to j equals 0, I want to check if it is smaller than that, but not further, right? And L of j is greater than value, right? If it's greater than, I want to shift to the right. In that case, I am going to shift j plus 1 to be equal to L of j. Shift the value 1 over. And subtract 1. Okay, so I is the value that I'm currently trying to put in a good place. Trying to find a home for I. So and then j, I start 1 and continue going until I find that this value is no longer smaller than this value, is no longer bigger than this value. That means I should stop here, right? So if I stopped here, then I need to put the value 1 above. This is the place where you actually mess things up. Okay, so that means I want to put the value that I want in Lj plus 1. Okay. Just to see if I'm doing this correct, I'm going to actually put some debugging here to show what L looks like at each step. And just to make sure that I'm actually not creating an infinite loop, I'm going to put a raw input right here. Okay? And I'm going to make this k smaller. I'm going to stop this for a second, and I'm going to actually try insertion sort of L. Okay. Just so that I can see if I'm doing this correctly. Whenever you have many, many loops, there's many places where you can have an infinite loop, especially a while loop. So just let's see if we did this correctly. Right? So let's see what that does. Okay, so I had this value. So I'm going to look at 1 and 3, they are in order. 3 and 9, they are in order. So now something interesting should happen because all of these values should shift, and I put 0 here. That worked. This worked. Okay. Now the places where you can mess this one up is if you forget that this is a stopping condition. This is what I did this morning. Or if you forget that you should put it in j plus 1, right? Because you keep subtracting. So generally when you finish, you're actually one step further, right? Because if you're inserting something between two values, you will stop here. So you want to put it actually to the right of that value. Right? So, assuming that this is correct, let us time it. So, I'm actually going to time insertion sort by sending the name of the function the same way I sent the other function, right? Yes? Function wrong, that's true. You're being too nice. I clearly have spelled it very wrong. All right. Okay, so obviously with 10 items, you are not going to see a difference, so let's try with 1,000 items. So, is it faster? How many orders of magnitude is it slower? So 1, 2, 3, almost like 1,000, right? Let's try adding another 0 here. Is it slower? Let's see how much slower it is. Take this value and divide it with this value. It is 2,816 times slower. Okay? So let us remind ourselves why it is n squared. Okay? So I run this algorithm n times for each value, right? So I'm going to run it for location 1, 2, 3, all the way to n minus 1, right? So I run this algorithm for every single location. The worst case is that if I'm in location 2, I may end up comparing location 2 with 2 different values, right? I may actually, if it is completely sorted in reverse, I may end up for each location 2, for example, location 1, I may have one comparison with 0. With location 2, I may have two comparisons with location 1 and 0, and so on and so forth. So this is the number of comparisons that I make in the worst case. So if you know your comparisons, if you know the Pascal, the Gaussian addition, this actually is n minus 1, n minus 2 divided by 2. Which is basically n squared, right? So it is n squared plus minus n minus 3n plus 3 divided by 2. Ultimately, all I care is there's an n squared in there. It is actually cheaper than some other n squared algorithms you may write, but it is not the best. Okay? So, questions? So let's try to write merge sort. Okay? The merge sort is going to be a little bit trickier to write, but it's not so difficult. And we are going to write a regular merge sort right now, but when we learn recursion, we are going to write a recursive version of it. Okay? After the break. So, the first thing that I need to write, this algorithm called merge. Remember, I was merging two lists. I want to take L1 and L2, assume that L1 and L2 are sorted, and then create a new list. So assume L1 and L2 are sorted, and create a new list, L, that is the merged version of L1 and L2. Okay? Now, could you take 5 minutes to try to write this algorithm? This algorithm you should be able to write easily. Okay? So, and then try it with simple functions like, try it with merge of 1, 2, and 3, 4. Okay? Try this for me. This algorithm you should be able to write very easily. How do you take the first element of a list? How do you remove the first element of a list? So if your list is, then you can actually remove the first element with pop, right? So always look at the first element, whichever is smaller, pop that, put it in the new list, continue until at least one of the lists is empty, then put everything that's remaining in that list into the new list. Okay, go. So when you're writing a function like this, it sometimes is easier to do it one step. Okay? Do it one step and then add the loop. So for example, I will start with an empty list. And if the first element of L1 is less than the first element of L2, what should I do? First, I will remove it from L1. Yes, but same thing. So I'm going to pop L1, 0, and then append the value. All right? You can technically do that in 2 steps too. Else, I am going to pop L2 and then append that to L. Okay? Does that make sense? Yes? No, you can say I'm going to append top 0, yes, of course. I'm going to actually change this in a bit, so that's why, but yes, you can. But it generally helps to break down a complex program into steps that you can read, unless you're creating really complex variables. Okay, so are you okay with this one step? Right? Okay, so now we are going to add a loop, right? We are going to iterate through this until what happens? Yes? Exactly. One of the lists is empty, right? So while, and we are going to write a while loop that is the opposite of that. While length of L1 is greater than 0, and length of L2 is greater than 0. That means I can pop from both of them, right? So at least they have at least one value. I will continue doing this. Okay. Then I am going to basically append whatever is left. At this point, I am guaranteed that one of the list is empty, right? So I don't actually even have to check which one is empty, right? I can write something like L.extend L1, L.extend L2. So what extend will do is take one list, append it to the other list, without creating a copy of the first list. If I were to do the plus, right? So if I do 1, 2, plus 3, 4, right? It's possible to take 2 lists and then combine them, but if I do that, it creates a copy of both lists. When you do extend, it only takes one list, makes a copy, and puts it in the end. And then I'm going to return L. So let's try and see if this is actually correct, right? So what I need to do is try it with various versions, so they are not the same length. Try it with one list has all the smallest values, which actually did work. Try it with a mix, like this is like this. Okay, so that seems to work. Now this is apparently turns out to be very costly. I did not know this until Professor Anna Milanova showed it to me. Pop is a very costly operation. Even though it's order of 1, it is a complex order of 1. So do I have to really pop things to put them in? Can I just keep track of where I am with an I and j? So I'm going to not use pop just to even be more fair. So I am going to have I and j to be locations of the last value. So instead of looking at 0, I'm going to look at the ith value. And I'm going to keep shifting I and j. So instead of doing this, if I is greater than, while I is less than length, and j is less than length, I'll put the other version online, but I want to update this one now. So instead of appending this, and I'm going to check L1 of I for L2 of j, instead of popping L1, just going to use the value, append that value, and increment I with 1. And then I'm going to do the same, but this time I'm going to append it with 1. Okay. Now, this one I'm going to do it slightly differently because now I need to look from I to end and j to end, something like this. Hopefully it's correct. You see that this is a slightly more complex way to do the same thing. So I did the simple one first, and then I have a pattern on how to do this. Now I'm trying the more difficult version, which is in no way guaranteed to be correct. Okay? So you need to try to see if it works for different things. It works for like this, okay? Seems to work. And I'm hoping that this is actually a simpler version. Right? So now what I want to do is use this to do sorting. Okay? So now we are going to do merge sort. So first, I'm going to create one list that has singleton elements of every single value. So I'm going to have a list L1. Then for value in L, I'm going to append in L1 a list of value. Okay, so this is the singleton values that I had before. And then I will keep now merging groups of 2 from this list. So I'm going to take 2 lists from this list of lists, right? So let's try this. Okay, so I have a list of lists first. Now I'm going to take 2 lists from here, merge it, put it into a new list until I am done with this list, and then I'm going to make that list my new list. Okay, I am not going to remove these 2 and then put it in. It just becomes too complicated to take care of it. So I'm going to use a new list. So what I'm going to do is, and again, I'm going to do this one time first. Okay, so I am going to start at 0, go up to length L in 2s, actually L minus 1 in 2s, right? So I'm going to create 0 and 1, 2 and 3, right? So what I want to do is I'm going to be merging I with I plus 1. So I'm going to be merging, for example, L of I with L of I plus 1. Okay, so I'm going to be merging 0 with 8, or let's do L1. I'm going to be merging list of 5 and 3, 9 and 0, 8 and 6. It may turn out that there is a lost element left, like we had, right? You have to take care of that. This will happen if you have odd number of items. Okay, we will do that in a second. So I'm going to take L2, which is the merged version of these 2. Okay, let's actually do L2. I'm going to call L merged. And then all right. So this is what I've done. I've taken the list. This is not really making any sense at all. Okay. Well, because I did not print L2. Okay. Well, once I've finished constructing L2, I'm going to actually assign it to L1, and I'm going to do this there again. Okay. So I took 4 and 9 merged, 6 and 7 merged, 3 and 5 merged, 2 and 0 merged, and 1 and 8 merged, but in the correct order. What happens if the list was odd numbered? In that case, I actually missed this last number, right? So if length of L1 is odd, then I am going to append L1's last element. Okay? So this is what happens. Okay, so does this step make sense? Construct singleton lists, merge them in groups of 2. So when you have a range, you can count in 2s. So 0, 2, 4. Merge in groups of 2, insert it to a new list, this L2, append it to this new list, and then change it back to L1 so that now I can use L1 again in the next iteration. So now I want to repeat this whole step in a while loop. And what is my condition? How many times do I want to repeat? I will keep merging until length of L1 is 1, because there's only one list left. There's nothing to merge it with, right? So while length of L1 is greater than 1, okay? There's a way to do this, hold on. There we go. Okay. And I'm going to return the first element, which is, this is a list of lists, L1 of 0. Okay. Now, it doesn't work in merge sort to actually do this, because to actually change the list, because I'm actually continuously creating new copies, so I actually am returning, so it's a slightly different one. But it doesn't matter when you're timing it. So, but let's try and make sure that it actually works. Okay, so let's run it a few times. It does not actually work, right? So, I think it has to be -2. No. All right, so now we have to debug. That is great. Okay. All right. Length of L1 is greater than 1. All right, so now what we need to do is since it's giving me error right here, print I and I plus 1. Okay. All right, so now I need to figure out what my error is. It says list index is out of range. So I need to know what are the I and I plus 1 that is giving me these two. So because probably I'm generating this range is incorrect. So let's see when that happens. Okay. And unfortunately, you have to generate enough test cases that this actually comes about. Okay. So in the first one, that works fine. Okay. And this time, 6, 7, it did not work. So let's see, I have 0, 0, 1, 2, 3, 4, 5. So length of L is 5. Why do I get 6 and 7? Ah, thank you. That is correct. Thank you. Great service to everybody. Okay. Saying, why this happens? All right. So let's see if that actually works. All right. I'm glad that worked out. All right. After you've convinced yourself that it kind of works, okay, now we can actually run our time function to see if actually it is better. So now I'm going to have, let's say 1,000 elements. Is it faster than insertion sort? Let's add a little bit more here. So it is at least 40 times slower, 40 times faster, right? Roughly 37, 40 times. Right, 3.6 seconds versus 0.1 second. But it's nowhere as close to the built-in sort, right? Because the built-in sort is actually compiled. This is why you learn C++. Just as a final step, okay, let us think about why it is actually cheaper. Okay, so what do? I take two lists. So let's look at merge. It takes two lists and merges them. So if you have k elements here and k elements here, how many comparisons do I make? At each step, I have one of the elements removed, right? So every element is compared at most one time. So you look at the smallest element, move it to the next. Next smallest, move it to the next. You can do this at most 2k times. So if you have two lists of length k, you can make at most 2k comparisons, right? You can do less because you may run out of one list and put everything else without really checking. And that is roughly still the number of elements kind of cost, but it's maybe cheaper because of using extend. Okay? So now let's think about the actual algorithm. So first I created lists of one item. Okay? So that was order of n. Then I merged n over 2 lists. I merged them, but each of these lists were length what? 1, right? So when I merged each of these lists, they were of length 1, so I actually had 2. 2 comparisons each time, right? So 2 comparisons for each merge. So when I'm done with this, right, I now have actually half the size of lists because now I merged each pair of lists. So if I had 16 lists before, now I have 8 lists. So now I actually have n over 4 lists to merge. Right? So now instead of merging n over 2 lists, I'm going to merge n over 4 lists because I have fewer left. And each time, each one is 2 and 2, right? Now I have groups of 2 and 2. So the merge is going to be at most 4 comparisons. The next time around, now I have even fewer lists, n over 8, but 8 each. So the point is that at each stage, I am doing exactly n comparisons, right? Every stage, I'm doing n comparisons. This is n over 2 times 2, right? n over 2 times 2 is n. n over 4 times 4 is n. n over 8 times 8 is n, right? So every single time I do a merge step for the whole list, I'm doing n comparisons. The question is, how many times do I do this? Well, I had n over 2, n over 4, n over 8. At some point, I'm going to come to n over n, right? When it's n over n, I'm done. How many times can you do that? Again, log n, right? Because every time you're reducing the size by half, you can only divide it by half log 2 n times. So you are repeating an n step thing, repeated log 2 of n times. Okay? So in fact, this is an example of an n log n algorithm. Right? Because you have n steps, but you only repeat it n times because you keep reducing the size of the things, number of things you have to do by half. So you have to stop after doing this for log n times. So almost all sort algorithms that you find are n log n, but you may still have more or less efficient versions by simple changes. Okay? So even though something is order of n log n, they may still be different in terms of cost, but for sure an n log n algorithm is cheaper than n square algorithm. Okay? So let's stop here.